Assalamu alaikum, dear students. I am Dr. Qurrat Ain Maqbool, lecturer Diet Sopor. I am going to deliver a lesson for class 11th on the topic carbohydrates, which is one of the subtopics of Unit 2 Biomolecules. Carbohydrates are the most abundant biomolecules on Earth. They are widely distributed in both plants and animals, where they serve different roles. Like, for example, they serve as food reserves in the storage organs in plants and animals. They are also an important source of energy required for various metabolic activities of the living organism. They also serve as structural elements in cell walls of plants. Plants are considerably richer in carbohydrates in comparison to the animals. Carbohydrates are also known as saccharides, which is derived from the Greek term saccharon, meaning sugar or sweetness. Since small molecular weight carbohydrates have a sweet taste, although this is not true for carbohydrates with large molecular weight. The name carbohydrate indicates that these compounds are composed of carbon, hydrogen, and oxygen, where the hydrogen and oxygen are present in the same proportion as they are in water. The name carbohydrate literally means hydrates of carbon. Many, but not all, carbohydrates have the empirical formula CH2O whole N, as some also contain nitrogen, phosphorus, or sulfur. A proper definition of carbohydrate is that they are polyhydroxyaldehydes or ketones or compounds which produce them on hydrolysis. Looking at the structure of glucose, it is evident that there are 5 hydroxyl groups attached to the carbon atoms and an aldehyde group representing the first carbon atom in the structure. Carbohydrates are generally classified into 3 major classes: monosaccharides, oligosaccharides, and polysaccharides, based on the number of sugar units they contain. Monosaccharides are called simple sugars that cannot be hydrolyzed further. They have the general formula CnH2O whole N. Oligosaccharides are small polymers of several monosaccharide units, usually from 2 to 10, joined together. Those involving 2 monosaccharide units linked together are termed disaccharides, and those having 3 monosaccharide units linked together are called trisaccharides. Anything larger is simply considered as an oligosaccharide. Polysaccharides, consisting of several monosaccharides, more than 10, joined together to form a single polymeric molecule. They may form linear chains of varying lengths, or they may consist of branched chain arrangements wherein two or more than two linear chains are joined together at a branch point. Both oligosaccharides and polysaccharides can be hydrolyzed by the action of acids or enzymes to produce smaller sugar units. Monosaccharides are further divided according to the nature of functional group present. Those sugars with aldehyde as the functional group are referred to as aldoses, and those sugars with ketone as the functional group are referred to as ketoses. Looking at the structure on the left hand side, the functional group is aldehyde, and so it is an aldose. And on the right hand side, the functional group is ketone, and so it is a ketose sugar. Based on the number of carbon atoms, monosaccharides are divided into trioses with 3 carbon atom, tetroses 4 carbon, pentoses 5 carbon, hexoses 6 carbon, and heptoses 7 carbon. As is evident from the table, trioses with 3 carbon atom have the formula C3H6O3, and glyceraldehyde is an aldose sugar with an aldehyde functional group, and dihydroxyacetone is a ketose sugar having a ketone functional group. Tetroses with 4 carbon atoms have the formula C4H8O4, and erythrose represents the aldose sugar and erythrulose represents the ketose sugar. Pentoses with 5 carbon atoms have the formula C5H10O5, and ribose is the aldose sugar and ribulose the ketose sugar. Hexoses with 6 carbon atom have the formula C6H12O6. Glucose represents an aldose and fructose represents a ketose sugar. Heptoses with 7 carbon atoms have the formula C7H14O7, and glucoheptose is an aldose sugar, while as cetoheptulose is the ketose sugar. The most abundant monosaccharide in nature is glucose. Both these characters, that is the number of carbon atoms and the nature of functional group present, may be combined while naming monosaccharides. For example, glyceraldehyde is a triose sugar with 3 carbon as well as an aldose sugar with aldehyde functional group. So both these characters can be combined together and it can be termed as an aldotriose. Similarly, dihydroxyacetone is a triose sugar with 3 carbon as well as a keto sugar with a keto functional group, so it can be named as ketotriose. Likewise, erythrose is an aldotetrose, erythrulose a ketotetrose, xylose an aldopentose, xylulose a ketopentose. Glucose is an aldohexose and fructose is a ketohexose. Asymmetry. All sugars possess asymmetric carbon atoms. An asymmetric carbon is one to which 4 different atoms or groups are attached. We can see that in the figure, 4 different groups R1, R2, R3 and R4 are attached to the carbon atom, and such a carbon atom is said to be asymmetric. The presence of asymmetric carbon atoms in the carbohydrates makes possible the formation of isomers in them. What are isomers? Compounds having the same molecular formula but different in properties because of the difference in the structure of their molecules are called isomers, and the phenomenon is called isomerism. If a carbon atom has 4 different atoms or groups projected into space in 4 different directions, it is possible to construct a similar figure simply by exchanging the relative position of any 2 groups. If you observe the figure keenly, you will notice that the arrangement of groups on the asymmetric carbon atom on the left-hand side is different from the arrangement of the groups on the asymmetric carbon atom on the right-hand side. These 2 models, which are shown in the current slide as well as the one we have discussed in the previous slide, bear the same relation to each other as that of an object to its mirror image. They are not identical because they cannot be superimposed one upon the other. If you place your left hand in front of a mirror, what you will notice that the image formed in the mirror is reversed sideways and it appears to be your right hand in the mirror. You have read about the phenomenon of lateral inversion in your previous class. According to this phenomenon, in an image formed by a plane mirror, the left side of an object appears on the right side in the image, while as the right side of the object appears on the left side in the image. So, if you try to place your right hand over the left hand, they will not superimpose upon the other. The relationship exhibited by such compounds is called stereoisomerism, and the 2 compounds are called stereoisomers. Stereoisomers are of 2 types, geometrical and optical. Optical isomers or enantiomers differ from each other in the disposition of various atoms or groups of atoms in space around the asymmetric carbon atom. The number of asymmetric carbon atoms determines the possible isomers for a given compound, which is equal to 2 raised to power n. The simplest carbohydrate, glyceraldehyde, has only 1 asymmetric carbon atom and exists in 2 isomeric forms. In 1891, Emil Fischer proposed that the stereoisomers of glyceraldehyde be represented by the Fischer formula as D-glyceraldehyde and L-glyceraldehyde. The form in which O hydroxyl group on the asymmetric carbon atom is on the right side is designated as D form, and the form in which the hydroxyl group on the asymmetric carbon atom is on the left side is designated as L form. What about those monosaccharides with more than one asymmetric carbon atom? These monosaccharides are also represented by the Fischer formula as D and L monosaccharides by taking D-glyceraldehyde and L-glyceraldehyde as the reference sugar. Hence, all the monosaccharides with the same configuration as D-glyceraldehyde for the asymmetric carbon atom farthest from the carbonyl carbon are given the designation D. Those that are like L-glyceraldehyde in this respect are called L-monosaccharides. Here again is the family of D-aldoses having from 3 to 6 carbon atoms represented by the Fischer formula. In all of these D isomers, the asymmetric carbon atom most distant from the carbonyl carbon has the same configuration as the asymmetric carbon in D-glyceraldehyde. Given here are the different isomers possible for aldohexoses, that is having 6 carbon atoms. Since the number of asymmetric carbon atoms present is 4, accordingly there would be 2 raised to power 4 or 16 isomers for them. Another kind of stereoisomerism exists between the aldohexoses. D-glucose differs from D-mannose and D-galactose by the orientation of the hydroxyl group only about a single asymmetric carbon atom. Such isomers are called epimers. If you can notice in the given figure, the only difference between the structure of D-mannose and D-glucose is the arrangement of hydroxyl groups at carbon number 2. So they are known as C2 epimers of each other. Again, comparing the structure of D-galactose and D-glucose, the only difference is the arrangement of hydroxyl group at carbon number 4. So they are known as C4 epimers of each other. So epimers are isomers of a given stereoisomeric family that differ in the configuration of the hydroxyl groups on asymmetric carbon atoms 2, 3, and 4. Optical isomerism. The presence of asymmetric carbon atoms in the compound confers optical activity to it because compounds containing asymmetric carbon atoms have the power of turning or rotating the plane of the polarized light, a light which vibrates in only one plane, either to the right or to the left. A compound rotating the plane of the polarized light to the right is called as dextrorotatory and is designated by small d or plus sign, while as a compound rotating the plane of the polarized light to the left is called as levorotatory and is designated by small l or a minus sign. The capital D and capital L designations do not indicate the direction of rotation. These symbols only refer to the orientation of the hydroxyl group on the asymmetric carbon atom. For example, D-glucose is dextrorotatory and is hence written as capital D with a plus sign, where capital D refers to the orientation of the hydroxyl group on the asymmetric carbon atom and the plus sign indicates that it rotates the plane polarized light to the right. D-fructose is levorotatory and is hence written as capital D with the minus sign, where again the capital D refers to the orientation of the hydroxyl group on the asymmetric carbon atom and the minus sign indicates that it rotates the plane polarized light to the left. Monosaccharides also adopt cyclic structures or closed structures because of the ability of aldehyde and ketone to react with alcohol to form hemiacetals and hemiketals. The carbon in the aldehyde group as well as the ketone group are not asymmetric, but after the formation of hemiacetals and hemiketals, the carbon now becomes asymmetric because now it has 4 different groups attached to it. In glucose, two types of cyclic or closed structures are possible when an aldehyde group at carbon 1 reacts with the hydroxyl group at carbon number 5. During the formation of these cyclic structures, a new asymmetric carbon has been created at carbon 1. The two structures having 6 members in a ring, 1 oxygen and 5 carbon atoms, differ from one another only in the orientation of the hydroxyl group at carbon 1. Again, in fructose, two types of cyclic structures are possible when the ketone group at carbon number 2 reacts with hydroxyl group at carbon number 5. Due to the formation of cyclic structures, a new asymmetric carbon has been created at carbon number 2. The two structures having 5 members in the ring, 1 oxygen and 4 carbon, differ from one another only in the orientation of the hydroxyl group at carbon number 2. Haworth, an English chemist, devised another method of representing the cyclic structures. Hence, a sugar with a 6-membered ring is known as pyranose in analogy with pyran, the simplest compound containing such a ring. The 6-membered ring has 1 oxygen and 5 carbon atoms represented in a plane. Sugars with 5-membered rings are designated as furanose in analogy with furan. The 5-membered ring has 1 oxygen and 4 carbon atoms represented in a plane. The cyclic forms of glucose and fructose with 6 and 5-membered rings are therefore known as glucopyranose and fructofuranose. Shown here is the Fischer and Haworth projection formula of glucose. In the Fischer projection formula, D-glucose is represented in the open chain form. It has only 4 asymmetric carbon atoms, carbon 2, 3, 4 and 5. In the cyclic structure, there are 5 asymmetric carbon atoms due to the creation of a new asymmetric carbon atom at carbon 1. The newly created asymmetric carbon atom, that is carbon number 1, is known as hemiacetal or anomeric carbon, and the cyclic structures are known as alpha D glucopyranose and beta D glucopyranose. In the Haworth projection formula, the bonds directed upwards and above the plane of the ring correspond to the left in the Fischer formula, and the downward orientation corresponds to the bonds which are shown as right in the Fischer formula. The carbon atom which is not involved in the ring formation, which is carbon number 6, are shown above the plane of the ring. The alpha and beta cyclic forms of D-glucose are known as anomers, as they differ from each other only in their configuration around the hemiacetal or anomeric carbon atom, that is carbon 1, and the phenomenon is called anomerism. Here also fructose has been represented by both Fischer and Haworth projection formula. In the Fischer projection formula, D-fructose is represented in the open chain form with only 3 asymmetric carbon atoms, carbon 3, 4 and 5. In the cyclic structure, there are 4 asymmetric carbon atoms due to the creation of a new asymmetric carbon atom at carbon 2. The newly created asymmetric carbon atom, that is carbon number 2, is known as hemiketal or anomeric carbon, and the cyclic structures are known as alpha D fructofuranose and beta D fructofuranose respectively. Carbohydrates possess active groups which are responsible for their chemical behavior. The properties of monosaccharides are based on the aldehyde group or the ketone group as well as the alcoholic groups present in them. Monosaccharides are easily oxidized by the oxidizing agents. With mild oxidizing agent, glucose yields gluconic acid, whose structure is shown at position 1. In this structure, aldehyde group has been oxidized to the carboxylic group. Glucose is also oxidized by the mild oxidizing agents to glucuronic acid, whose structure is shown at position 2. In this structure, alcoholic group at carbon 6 is oxidized to carboxylic group, while as the aldehyde group remains unaffected. With strong oxidizing agents, both the aldehyde group and the alcoholic group at carbon 6 is oxidized to carboxylic group to yield the dicarboxylic acid glucaric acid which is shown at position 3. Carbohydrates that have free aldehyde or ketone groups function as reducing agents. Glucose and other sugars capable of acting as a reducing agent are called reducing sugars. Monosaccharides are more active reducing agents than the disaccharides. A reducing sugar will reduce another compound, for example, the cupric ions present in the Fehling solution to the cuprous ion, and in this process, the carbonyl carbon of the sugar is oxidized to a carboxylic group, producing an oxidized sugar. So the reaction can be represented as reducing sugar plus cupric ions will yield an oxidized form of the sugar and the cuprous ions. This reaction is useful in the estimation of glucose and other reducing sugars, that is, those sugars containing a free aldehyde or a ketonic group. Free aldehyde and ketone groups of monosaccharides can also be reduced to the corresponding alcohol groups. The reduction of a simple sugar with hydrogen gas under pressure in the presence of a metal catalyst converts the carbonyl group to an alcoholic hydroxyl group. For example, D-glucose on reduction will yield D-sorbitol, where the aldehyde group has been reduced by the addition of hydrogen atoms to the corresponding alcoholic group. Same way, mannose will yield mannitol, galactose will be reduced to dalkitol, and glyceraldehyde will be reduced to yield glycerol. So, dear students, in this topic, hopefully, you must have learnt the definition of carbohydrates, their classification, the structural representation of monosaccharides, both open chain and ring form, the phenomenon of stereoisomerism, and the redox reactions exhibited by the carbohydrates, which forms the basis for the estimation of reducing sugars. Thanks.